So next, the load line analysis in the common emitter configuration. I told you that the common emitter configuration is basically the amplification, right? Related to the amplification. So where we are using for the amplifier, there we are using this circuit. So this is a typical circuit of using as an amplifier. It is an NPN transistor, and you can see that this is the input characteristics. This is the forward bias. So where is the IB versus VBE, the base to emitter voltage. We can get the slope. From this slope, it is 1 by RB, that is the input resistance. So it is a transconductance. We can find out the transconductance from here. And this, the equations from this input loop, you see, in the input loop we are using the Kirchhoff's voltage law. Please understand, when we will solve the problem, the exercise problem, then this is very important to understand. So here you see the input voltage is VBB and another is the Vin, that means the AC signal which we want to amplify, right? So is equal to what? RB and IB. RB plus IB is basically the potential drop across RB will be this RB-IB plus the potential drop in the junction base to emitter junction, right? That is VBE. So ultimately we are supplying this voltage VBB and V in D. VBB is in DC mode and V in is typically the AC mode, the signals which you want to amplify, right? And then according to the Kirchhoff's voltage law, that should be equal to summation should be, we know that it should be 0. So based on this, that part should be equal to RB IB, that means the potential drop across RB and the potential drop across base to emitter junction. Okay, so that is the input loop. And here if IB is equal to 0, because it is in the microampere, so what we can write, that VBE is equal to VBB plus Vin. That means the applied the DC voltage for biasing, and Vin is the input signals which we want to amplify, right? So if VBE is 0, again the conditions, if I'll put VBE is equal to 0, that means base to emitter is 0, then what we will get, IE, the emitter current, is equal to what we can get, sorry, it is base current is equal to VBB plus Vn by RB. So it is IB, right, the base current. So that is, we can get it from here. So this is kinds of analysis in the input characteristics part, that means this part. Now we can consider in the output part how we can do the analysis. This is called the circuit analysis. So the circuit analysis, please understand, otherwise it will be very tough for you to understand, to realize the same. So here is the same circuits we are given. Now we will concentrate on the output loop. In the output loop, you know that here, what is this? This is basically the output characteristics. So we will do the straight line. How we can draw this straight line? So for that, what we have to do, that in this case, what is the voltage? The VCC is the voltage, right? And when we are apply the DC bias, the VCC, which is basically balanced with ICRC, that means the potential drop across RC, this one, and the potential drop from collector to emitter. So applying the KVL in the output loop, the Kirchhoff's voltage law, then we can say the VCC is basically the summation of ICRC, that means the potential drop across collector resistance, and the potential drop across the collector to emitter junction. So collector to emitter junction, it is not possible. So collector to emitter means collector to base to emitter junction, right? So the VCE is basically, we are using VCE is the output voltage. So if I write this, it is, you can see it is the representation of a straight line, right? Y is equal to mx plus c, right? X is the, here you can see, if I'll put 0, VCE means if 0, here it is 0. So there is no potential drop here. Then what will happen? We will get a straight line, and the slope, from there I can get the slope, that VCC is equal to minus ICRC. So we can find out that IC value, right? In the IC is nothing but a VCC by RC. From this equation we can find out, right? VCC divided by RC is equal to IC. So when VC is equal to 0, then we can get this point. When IC is equal to 0, that means this point. When IC is equal to 0, if we will put in this equation IC is equal to 0, then VC is equal to VCC. So we can put there the VCC. So ultimately we will get a straight line, and this straight line is very, very important. Here the intersection with the output loop, we will get the different operating point, right? And when we will use for the amplification part, we have to select which one will be more getting more effective, that we have to choose from the load line. So this line is basically saying the load line. So the load line will intersect in different points, and these points are called the Q1 or the operating point that we will discuss. From there we can get the amplification that I will discuss in the later slide. Okay, so that is the analysis. I think it is very clear. So I am telling again and again, the transistor configuration, the transistor is very uh, not very easy or simple, so I tried to make it simple. Okay, next is the BJT operation. There is a cutoff. Now when we have the cutoff region, then there is two junctions we know. One is the emitter based junction, another is the collector based junction. So in the cutoff region, the emitter based junction will be in the reverse bias mode, and the collector based junction will be the reverse bias mode. So what we are using this for the switching application in the digital circuits, that means the 0 1, this concept, that the digital circuits we will use the things. And the saturation region also, but the saturation region, it is also, we will not, these two are in the forward bias, the emitter based junction and the collector based junction, maybe they are the forward bias. So ultimately there will be no current flow, so it will not in the, we will not get, only we were getting the, it is just like a ohmic region, so there we cannot use for any purpose, right? Active region is basically, but we can use for only switching, that means 0 and 1, where this is a transition point. The active region is basically forward and reverse. This is the ideal one, that where we can use for the amplification, that means the emitter based junction should be forward bias and the collector based junction should be reverse bias, that means in the active mode, right? And the reverse active, that is the reverse, the electron based junction will be reverse and the collector based junction will be forwards, that is a performance degradation, means we cannot use this part, also is not usable, right? That's why I told you that please understand that when we will use, that is basically we have to use in the active region, that is the electron emitter based junction should be forward bias and the collector based junction should be reverse bias. Okay, so that is there we can get only the gain, that is the amplification. Now the realization of amplification, that is I can show you what I told you, very interesting. You see there is the load line, I told you Q is the operating point. So here we are using the input signals in the input circuits, we are applying the voltage, the signals, the input signals, that is the V in, that is the V in. Okay, so it is in the base region. Now what we will get here, you see this is the base region, I base is equal to 200 microampere, this is the current, and this one is the output characteristics. You can see the output characteristics, and after that we draw the load line. What is the, how we can draw the load line, I already explained. This side is VCC by RC and this side is VCC, right? This point is the VCC, so we can easily draw the load line. So the load line will intersect in different points on the active, in the active region of the output characteristics. So we have to find out, and the middle one, if you'll consider the middle one, that is called the operating point or Q point, quotient point. So this is when we are applying the base amplification, the base voltage, then we can get the amplification, and you can see this is the after amplification, the voltage amplification. So from here it is very clear, just you see that is the input signals and this one is the output signals. So the output signals we will get from the collector, so it is the collector, the VCE, and with the collector current. So from there we can easily say it that in our the our point A and point B is corresponding to the positive peak. This is the positive peak and this is the negative peak respectively. So the graph shows the ideal operation. Okay, now I am going to discussing one problem, the exercise, that is the determine IB, IC and IE, VVE with these circuits. Okay, so now when the base emitter junction is forward bias, then you can see this is a NPN common emitter NPN transistor. Here it is for the amplification. Here it is given the RB means the base resistance, and this is the collector resistance 100 ohm, and there you are applying the output voltage, that is the 10 volt, and the base voltage, that means the input bias, is the 5 volt. So when the base emitter junction, we what we have to find out, the IB, IC, IE, VVE, VCE, VCB, all things. So what we will do, when the base emitter junction is forward biased, then VV is equal to 0.7 volt. So what we are applying here, the Kirchhoff's voltage law. So in the input sector, I know I already discussed that VBB, and there is a VBE, basically the base to emitter potential drop, base to emitter junction and the base to emitter junction. So what the voltage we are using here, VBB, that is basically utilizing across the potential drop across the RB as well as the VBE. So here you can see that IBRB plus VBE is equal to VBB, and from there we can get the IB 430 microampere. So we can find out the IB from here. The similarly IC is equal to, you have the beta, so the common emitter current gain, it is already mentioned, so you can just put this, then you can easily find out IC. And again IE is equal to IC plus IB, so you just put this, then you can find out the IE. So you will get IEB, IC and IE. Next you have to find out VBE. So the VBE, you know the IB, so you know the RB also, so you can find out easily the VCE and VBE. So the VBE is for in this case we are using the VBE 0.7 volt because it is in the forward bias and silicon. So when it will not mention anything, then you can think it is a silicon diode. So if it is a silicon diode, then we know the cut-in voltage is 0.7 volt, and that is the base to emitter junction. So it is always it is a thumb rule that VBE, the base to emitter junction, will be 7 volt. So you got it. So then VCE, now we are coming to the output loop. In the output loop, you know that VCC is equal to ICRC, because RC is the potential drop across the RC, that is ICRC, and plus VCE. VCE means the collector to emitter potential drop. So then we can put it this, then we can find out the collector to emitter potential drop. So you will get the collector to emitter potential drop. So if you know this, then VCB also you can find out, because it is, I already showed you in the previous slide that this is the VBE. Yes, it is the VBE, this one is the VCE, and this one is the VCB. So the VCB plus VCE is equal to VBE, this one is the VBE, this one is the VCB, is equal to the VCE. So from there we can find out the VCE. So these are all we can find out easily. So applying Kirchhoff's voltage law to find the parameter I already discussed, and I think it is clear. If you not understand, then maybe you can listen several times, then you can understand easily. Okay, so this is the exercise. Now again there is another exercise I have just want to point out here. Here the determine the voltage gain of the AC output voltage in figure if emitter resistance is RE. So emitter resistance is given and the other things are already given. So if you see the amplification refers to a small change, so the voltage gain, we will just find out the voltage gain, that is RC by RE, because it is a common emitter NPN transistor. So here the configuration is this, so we can get the AV is equal to RC by RE, and that is basically the 20. So if I'll get the AV, so we can find out VB. From there we can find out the AC output voltage, and the input voltage is this corresponding to the output voltage. So I think this is easier for understand. So due to the limitation, I just not too much discussing on that. You can easily understand the steps here. Next, the advantages of BJT. What is the advantages of BJT? That high driving capability, high frequency operation, digital logic family, and there is low forward voltage drop. So that the advantage. What is the disadvantage? Every electronic component has pros and cons, right? So the disadvantages is that it has very complex base control and may lead to confusion and hence requires skillful handling. So that is the important things. That's why I discuss these things in so given so more uh, stress on the discussion, because the bipolar junction transistor is very complicated, and once you understand or realize that what is the bipolar junction transistor and how you can analyze the circuits, then it will be very easier for your future, because when you will design any circuit for based on your input and the output, then you should understand the circuit knowledge, you should get the circuit knowledge. There you are using in these circuits you will use a lots of BJT. It is not like that you can just avoid the BJT there. So if you have the circuit knowledge, if you have this, then you can easily understand that where you will use which component such that you will get your desired output, right? So that is the things. Now I'm just given the applications wise. The amplifier which we are discussing here, it is, I don't need to discuss more. That amplification occur, I already discussed step by step. Next is the logical switch. Here the logical switch, we are using the same. You can see the common emitter configuration, and this is the collector current, and this is the there we are using the logical switch. This is a logical switch. When it will be connected to the collector to emitter, then we can get, that means in the cutoff region we have to use this. So then we can get the performance of the switch. Okay. Next is the voltage regulator. Yes, this is very important. The common base, you see the common base configurations they are using here. So the voltage regulator is the power transistor. So here we are basically interested to use this circuits. So here the main concept to use this to sustain the power. So that is we will use the voltage regulator. And last is the phase shifter. You can remember that in the in case of common emitter configuration, there will be the 180-degree phase difference. So if I want to get the 180-degree phase difference, then we can use the phase shifter where we can invert the output, and this is sometimes it is very important. So these are the major applications of bipolar junction transistor. One is amplifier, another is logical switch, another is voltage regulator, another is phase shifter. So these four are the major applications which I just want to point out here for your understanding. Okay. Next is the transistor testing. So the transistor testing is very important, that how you can know that which one is the emitter, which one is the base, and which one is the collector. Through the multimeter, digital multimeter, you can easily find out, because you know that there is the two things. If it is a low resistance occur between base to emitter, because if you give the forward bias, then it should be the low resistance. And similar things happen in case of base to collector, there the reverse bias. If you give the reverse bias, if it is a high resistance will occur, then basically this part is the collector region. This is the collector lead and this is the base. So you can easily identify that how the things are happening using the ohm meter or the digital multimeter. So from there you can easily understand the things. Another is the curve tracer. So these are the testing system, the how you can know the transistor which lead is which when you will put. Also there is another way, if it is a metal cap transistor, then generally the metal cap is the collector which the it is by default, and if it is just you put it in the you know that like this way, the isosceles triangle, then the collector you can easily find out, because the lead with the collector with the the metal cap, it will be the shorted. So from there you can identify the collector, and then the near to the notch it will be another one. So like this way there is a lots of convention when you will use for transistor in a circuit, when you will do the real time operation, at that time you should understand it in the circuit level, such that you can identify and put it in the proper way. Okay, so that is the things of the transistor, but a lots of things are there also which I have not covered due to the time constraint. So you can feel free to ask the question through email. My email is somnath@gmail.com. So if you like, you can communicate with me. I am ready to help you. Thank you very much for your kind patience.